I'm going to look a little bit at radicals and rational exponents here. There are going to be two mini lectures that go over this topic. This is part one. And we're going to start out talking about square roots, which I'm sure you've seen before. We have this relationship, if I take 5 to the second power or negative 5 to the second power, in both cases we get 25. In that sense, then I can say that both 5 and negative 5 are square roots of 25. So in general, if b squared equals a, then b is a square root of a. So 5 squared is 25, so 5 is a square root of 25. b is a square root of a. And we use this radical symbol without any sort of index. And there's no number written here. Eventually there will be. When we use that symbol, we actually mean the positive square root. That's sometimes also called the principal square root. So if I used a square root symbol up here, and I said the square root of 25 with a radical symbol, that would just be 5. It wouldn't be the negative 5. We'll see here in part B below how I can talk about a negative square root if I want to. So in example 1 here, I'm just doing some simple square roots. Part A, square root of 81. Since that is a square root, what I really want to think is what squared equals 81. And of course, I know that would be 9. So I just say the square root of 81 is 9, because 9 squared is 81. In part B, that negative on the outside, right here, that negative is going to stick around through the rest of the problem. And so that's going to make my answer negative. When I take the square root of 121, that's going to end up being a positive number, and then the negative in front is going to make the whole answer negative. So again, what I'm going to think here is what squared equals 121. Well, I know 11 squared is 121. So when I'm doing this problem here, the negative comes down, and then the square root of 121 is 11. So my answer is just negative 11. In part C here, the 9 plus 16 is inside the radical symbol. The radical symbol is a grouping symbol as well as a square root symbol. So I need to do what's inside first. So I'm going to have to take 9 plus 16 and get 25 before I do anything else. And then, of course, I think what squared equals 25. And so I get an answer of just 5. In part D, the plus is not inside the radical. I have two separate radicals, so I have to do the radicals first. So I think what squared is 9 and what squared is 16. So that's going to give me 3 plus 4, which is 7. And one important thing here, if you look at part C and part D, notice I can't do part C by taking the square root separately. I can't just take the square root of 9 and then the square root of 16 and get 3 and 4, because if I add those together I get 7. Whereas here I have to do 9 plus 16 first and get the square root of 25 and get 5, and these obviously are not the same results. Now, in this case, a number that is the square of a rational number is called a perfect square. So in example 1 here, all of these were perfect squares. 81 was a perfect square, 121 was a perfect square, 25 was a perfect square, 9 and 16 were perfect squares. We have a little bit of a problem that can come up. If I wanted to evaluate the square root of negative 25, I need to find a number whose square is negative 25, but there's no real number that acts that way. Right? A negative times a negative is a positive. I need something times itself that's a negative, and I don't know how that works. We say here square root of negative 25 is not a real number. Now, this note here, I took this from another class, so it's not going to be section 1.4. That's not where we're going to talk about this. We're actually going to talk about this a little bit later when we talk about complex numbers. One other thing that sometimes comes up, if I have the square root of 4 squared, well, square root of 4 is 2, 2 squared is 4. So the square root of 4 squared, those things undo each other and I just get 4. So in the same way, if I had the square root of 5 squared, that should be 5 as well. And in general, if I have the square root of a squared, that's just a. It really only works if a is non-negative, so that means a has to be greater than or equal to 0. A can't be a negative number, it can be 0, or it can be positive. Let me go to the next page here. All right, other kinds of roots. So we have nth roots of a. This little n that's written here is called the index. And if I have something like just the square root of 25, that really is let me rewrite that. If I write a radical without an index, without a little number here, it's assumed that that number is 2, and so that means I'm looking for perfect squares. If I have an n there, some other number other than 2, then I'm not looking for perfect squares, but perfect powers of n. So perfect third powers, or perfect fourth powers, or perfect fifth powers. Otherwise, it works the same way. If I have b to the n equals a, then b is equal to the nth root of a. So I need a number that I multiply together n times to get what's in the inside. All right? So when I look here at example 2, part A, I've got an index of 3, so that means I'm looking for a perfect third power. So I want to say what to the third power is 64. And you can try different things, but if you try 4 times 4 times 4, that ends up being 64. So that means this cube root of 64 is just 4. Okay. Part B, we would have what to the third power is negative 343, right? Because it's an index of 3, right? So I need 3 things multiplied together, something 3 times, giving me negative 343. Well, if I try some different numbers here, 3 times 3 times 3 is 27. That doesn't work. If I try 6 times 6 times 6, that's 216, getting closer but not quite. If I do 7 times 7 times 7, that's 343. Now, of course, the only problem is, so that number matches up, but it needs to be negative. On the other page, when I had the square root of a negative, that didn't work, because I couldn't take something times itself and get a negative. But here, what if I made the 7 negative in this problem? If I took negative 7 times negative 7 times negative 7, well, 7 times 7 times 7 would still be 343, but now I have a negative times a negative, which was positive, but then times another negative, so that would be negative 343, and that's what we want here. So my answer would be negative 7. So part C, here I've got a 4 as my index, so that means I want a fourth power. So I think what to the fourth power equals 256. Now, since it's even, I probably would have to start with an even number. If I do 2 times 2 times 2 times 2, that's 16. That's not big enough. If I do 4 times 4 times 4 times 4, you can use a calculator to help you if you need. That is 256. It is the fourth root then of a positive number, so this does give me a positive. So my answer is just going to be 4. And finally, in part D, I have a fifth root here, right? I got a 5 as my index. So I would say what to the fifth power equals negative 243. Well, fifth powers get pretty big pretty fast. If I try 3 times 3 times 3 times 3 times 3, well, that's 3 times 3 is 9, 9 times 3 is 27. Again, you can use a calculator. 27 times 3 is 81, 81 times 3 is 243. The difference, of course, then here, though, is I need my answer to be negative, and since there are an odd number of numbers multiplied together, that will work as long as the 3 itself is negative. So my answer is negative 3. So we have some patterns here that I've described on the bottom. Remember, if I had something like the square root of negative 25, or if I have any even root, fourth root of negative 256, these won't work. These end up not being negative real numbers. There's something we call complex numbers that we'll look at a little bit later. But I can take an odd root of a negative number or an odd root of a negative number. So, an even root of a positive number is positive. An odd root of a positive number is positive. An even root of a negative number is not real. An odd root of a negative number ends up being negative. And so that's what I've got down here. If we're taking even roots, we can take even roots of positive numbers and we get positive numbers as my results. But I can't take an even root of a negative number. We say that's undefined. If I have an odd root, my index is odd, well, an odd root of a positive number is positive. An odd root of a negative number is negative. Let me go to the next page. We have another way of representing this idea of roots. We certainly know the square root of 7 squared would be square root of 7 times square root of 7. It sort of makes sense. 7 times 7 is 49, and the square root of 49 is 7. And we, of course, said square root of 7 squared. Those undo each other. I just get back to 7. But if I would take 7 to the 1/2 squared, that would be 7 to the 1/2 times 7 to the 1/2. Now, we haven't dealt with 1/2 as an exponent before, but when I did this with exponents, if I had the same base that I'm multiplying together with different exponents, I just add the exponents together. 1/2 plus 1/2 would be 2/2, which is 1, and I just get 7. So square root of 7 times square root of 7 is 7. 7 to the 1/2 times 7 to the 1/2 is 7. 7 to the 1/2 and square root of 7 are acting the same way here, right? They both give me 7 when they're multiplied by each other. So in that case, the square root of 7 is the same thing as 7 to the 1/2 power. Whatever this number is in the bottom ends up being the root. So if I have a to the 1 over n, I can just stick a little n as my index and rewrite it that way as a radical. So down here, 81 to the 1/2 power, that would be a radical with an index of 2. Now we normally don't write that index down. We would just say the square root of 81, which would be 9. Whereas then in part B here, that would be the cube root of 125. So I think what to the 3rd power is 125, and that would be 5 times 5 times 5. Here, I've got 1/3 power, like I did up here. That 3 again, whatever's in the denominator, just like that n, that becomes my index. So this is going to be the cube root of negative 27. So that says what to the 3rd power is negative 27. I think that would have to be negative 3. Right? Negative 3 times negative 3 is positive 9. Positive 9 times another negative 3 would be negative 27. And here in part D, 32 to the negative 1/5 power. Now, there's two things here. This 5th is my root. The negative, we have to go way back and remember negative means I take the reciprocal. So I can actually rewrite this as 1 over 32 to the 1/5 power. So that would be 1 over the 5th root of 32. And so I have to think what to the 5th power equals 32. And I think 2 works, right? 2 times 2 times 2 times 2 times 2. So that would just be 1 over 2. So, in example 9, that's not example 9. In example 3, all the rational exponents had a numerator of 1, right? 1/2, 1/3, 1/3, 1/5. This is not always true. If not, we can do something like this. 8 to the 2/3. I can think of this 2/3 as a multiplication problem. If I have a power of a power, I would multiply those exponents. 1/3 times 2 would be 2/3. But 8 to the 1/3, this 3 is my root. That would be the cube root of 8. And the 2 goes along for the ride on the outside. So when I take the cube root of 8, I get 2. And then 2 to the 2nd power, 2 times 2 is 4. That's one way I could do this problem. Another way I could do it would be to rewrite it with the 2 on the inside and the 1/3 on the outside. What this does, it generally gives bigger numbers, though, if I take the power first. So 8 squared is 64. 64 to the 1/3, that's my root. That would be the cube root of 64. What times what times what is 64? That would also be 4. So when I see this a to the m over n, just like here with the 8 to the 2/3, in both these cases, 3 was my denominator. I took a cube root of 8 or a cube root of 64. 2 was my numerator. I either took something squared here or something squared here. So the numerator was a power that I took, and the denominator was a root that I took. And so that's what I can write in here. The numerator is always the power, and the denominator is always the root. So, a few more examples on page 4. So, rewrite using radical notation and simplify if possible. So, remember, the numerator is the power, the denominator is the root. So, I would rewrite this as the square root of 36, that's my root, and then I would take the power to the 3rd power. I always take the root first because it gives smaller numbers. If I did it the other way, I'd have to start with 36 to the 3rd power, and that's a really huge number then that I'd have to take the square root of. But here I just get the square root of 36 is 6. 6 to the 3rd power is just 6 times 6 times 6, which is 216. Negative 27 to the 5/3. So again, this 5 is a power, and the 3 is a root. In general, I want to take the root first. So I'm going to get the cube root of negative 27, and then I'm going to take that whole thing to the 5th power. So I think what times what times what is negative 27. So 3 times 3 times 3 is 27. So I get negative 3 to the 5th power. So that's going to be negative 3, negative 3, negative 3, negative 3, running out of room here, negative 3. And that ends up being negative 243. Part C with 32 to the negative 2/5. First of all, the fact that that's a negative power means that I'm going to take a reciprocal. So that's going to be 1 over 32 to the 2/5. The 2 is my power. The 5 is my root. So I'm going to get 1 over the 5th root of 32, and then take that whole thing to the second power. So I need to think what to the fifth power equals 32. Turns out 2 works, right? 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and finally 16 times 2 is 32. So the fifth root of 32, right, this stuff inside the parentheses, that just gets replaced with 2, and I still have the exponent 2 on the outside, so that ends up being 1/4. And finally, this last one, there's no computations here. What's really important in this one is realizing that the 1/3 here as my exponent only applies to the m. This is really 4 times m to the 1/3. So order of operations says that the exponent takes priority over the multiplication. So this 1/3 only applies to the m. So that's going to be 4 times the cube root of m, and that would be all I could do with that problem.